Okay, so the second key lever for functional analysis involves this extended second fundamental theorem of calculus. We've seen this a lot in multiple choice settings where you're asked to take the derivative of an integral and you see a function as your upper bound. And we are allowed to just take that upper bound and drop it into the function of f that's sitting inside of our integral, and then multiply out by the derivative of that g of x function. We can also see this in free response style questions, which is what I want to walk you through right now, and this just allows us to raise the bar a little bit in terms of rigor on these functional analysis questions. Okay, so here we go. We have a continuous function f that's defined from -4 to 3, and our graph consists of 2 quarter circles and 1 line segment. G of x is equal to 2x plus the integral from 0 to x of f. We want to first find g of -3. There's nothing too rigorous about this one. And then that second piece is where our second key lever will come in. So for g of -3, I'll do that over here. That just means take the g of x function and drop in a -3 everywhere we see an x. So that creates this expression here, 2 times -3 plus the integral from 0 to -3 of f. So I'll do some simplification and I get -6 plus, this is the area from 0 to -3 of f of t. And maybe it might make more sense for us to change this to a negative integral from -3 to 0 so that our bounds are in the right order of f of t. So that's -6 minus the area of that quarter circle. So pi times our radius squared over 4. Our radius is 3, so I can drop that 3 in. A simplified version of this would be -6 minus 9 pi over 4. And there's nothing else we have to do for that first point. The second part of this asks us to find g prime of x and evaluate that at -3. So to find g prime of x in slow-mo, what we're going to be doing is taking the derivative of g of x, which is 2x plus the integral from 0 to x of f of t dt. So the derivative of 2x is just 2, and then the derivative of the integral from 0 to x of f of t is f of, big reveal here, x, because we drop that upper bound in and then we multiply out by a 1, which doesn't really impact our equation. So g prime of x is equal to the function here, 2 plus the integral, 2 plus the function f of x. So now if I want to find g prime of -3, I just have to plug into this equation. That's 2 plus f of -3. I use my graph and I realize quickly that f of -3 is right here on the x-axis. So that's 2 plus 0 for a final answer of 2. Alright, so in part B, we're again asked to determine the x-coordinates at which our original function g has an absolute maximum, and then we need to justify our answer. So just like last time, when I see absolute max, I'm interested in trying to find those critical points and endpoints to help me assess where it is that my function takes on its maximum quantity. So I'm already kind of thinking ahead to setting up a little table for myself that captures x values and g of x values. And in this case, I know that my table is going to be anchored at -4 and 3. The tricky part is establishing those candidates, critical points, in other words. In the last problem, just got to look for where my derivative was equal to 0 on the graph. That was looking at the x-axis where we crossed. In this case, it's going to be a little more complicated because our derivative that we just established is actually equal to 2 plus f of x. So I do most definitely want to find my candidates by understanding where my derivative equals to 0. But on this problem, that means where does my derivative equal to -2 when I do some rearranging here. So -2 looks to be right around here. So the other candidate is going to be right over here where my function intersects the horizontal line -2. So I have to do some analysis here to try and uncover what coordinate point it is that those two things equal to one another. So I'm going to look at this line real quick and see if I can do a quick slope calculation. I've got a point up top of 0, 3 and a point down low of 3, negative 3. So a quick change in y over change in x, I think, is negative 6 over 3 or negative 2. So that line right there actually has a slope of negative 2. And if I look closely, it's got a y-intercept of 3. And the way to solve this is to set that line equal to negative 2 so that I can uncover when that piece has a y value of negative 2. Do some rearranging, move the 3 over, divide by negative 2, and it looks like the x value where my derivative is equal to 0 is at x equals 2.5. And just with a quick scan of my graph, I believe that. It looks to be between 2 and 3. Okay, so now what I want to do is take each of these values and see if I can identify what the output is on our original graph at these 3 points. So let's see. We'll start with the bottom, and we'll try and find g of 3. That's going to be 2 times 3 plus the integral from 0 to 3 of f of t. So with a little bit of math, I get 6 plus the area from 0 to 3. This is just great because the area from 0 to 3, I've got one triangle that's positive and an identical triangle that's negative, so that cumulative area is 0, and the output at 3 is just equal to 6. I'll try 2.5 now, so that's going to be, g of 2.5 will equal to 2 times 2.5 plus the integral from 0 to 2.5 of f of t. So 2 times 2.5, that's 5. And this time the area from 0 to 2.5 looks to be, let's see, the positive triangle minus that negative triangle. So I'm going to pause real quick to do some calculations. I'm going to come back to you in a minute with that cumulative area. All right, I'm back, and I actually got an area here of 5/4 for the 2 triangles in question. I'll try to highlight them so you can see what I'm looking at. I had to do this one up top, and then not the entire yellow down low, but just to 2.5, so that little guy right there. And I think I got 9/4 for the one on top, so I had an area up here of 9/4. And then the one down low, I got an area of -1 because we're below the x-axis. Some common denominators, and I was able to come up with this, which in decimal form, since that's what you people seem to like, 6.25 is what I got, which is really interesting because that's a value just slightly larger than our endpoint at 3. Okay, so then the last thing that I want to do is uncover the quantity at -4. So g of -4 is 2 times -4 plus the integral from 0 to -4 of f. All right, so this one gets me to a -8. And let's be careful here. My bounds are upside down. So if I flip those bounds, I'm actually going to be subtracting this large quarter circle and adding this smaller one. So I'm at -8 minus 9 pi over 4 plus pi over 4. And even without simplifying, I'm able to realize that that's a pretty large negative number because I'm at -8 and then I'm subtracting a big quantity and adding in just a little bit. So I can do some quick number sense, and I'm able to capture here that my maximum quantity is at 2.5 and the value is 6.25. So to determine the x coordinate at which g has an absolute max, we have an absolute max of 6.25 occurring at x equals 2.5. So that's kind of a doozy. You can see how this complicated integral really made that absolute max question much harder. Okay, so next I have our typical point of inflection question. So I want to know when G has a point of inflection. Just as a reminder from earlier, that's going to be when G prime changes from increasing to decreasing, or vice versa, decreasing to increasing. So let's remind ourselves real quick. G prime we defined as 2 plus f of x. So I'm looking at a graph of f of x right here, and my derivative function is actually 2 more than that. So just speaking algebraically here, it's like I'm taking every coordinate point and just shifting them up 2 units and then trying to generate that same type of picture. That's my derivative in red. So the good news is it looks identical to the black curve, just shifted up a couple units. So where does my G prime, my red graph, change from increasing to decreasing or decreasing to increasing? Right here at x equals 0. That's the answer to this question. So at x equals 0, G has a poi because G prime changes, specifically in this case, from increasing to decreasing. That'll do it. Okay, and last problem here, we want to find the average rate of change of f on the interval -4 to 3, and then they tell us that there's no point for which f prime is equal to that average rate of change, and we want to explain why that does not contradict our mean value theorem. So let's start with the average rate of change of f. So the function's name is f. So that means I want a change in f's y's over a change in the x's. Simplify the bottom first, that just looks like 7. And up top, f of 3, according to our graph of f, is -3, minus f of -4, according to our graph, is -1. So I get a slope of -2/7. And the reason that there's no place where my derivative is equal to that slope on this interval, there's nowhere where I can generate a parallel line, is because I have some places that are non-differentiable on this graph. Specifically, if you want to get into details, we're not differentiable here at the cusp and over here where there's a vertical tangent line where those 2 quarter circles meet. So MVT is not contradicted because f is not differentiable at x equals -3 and x equals 0. Therefore, MVT does not apply to f on the interval -4 to 3. So just recapping what we saw earlier here, stating why MVT can't hold on some of these interesting piecewise graphs is typically because of non-differentiability. All right, so that's the end of that free response. What I want you guys to do, whoops, not that. What I want you guys to do for me is to come back to your packets, and there are some check for understanding multiple choice practice problems that highlight many of the derivative and functional analysis relationships that we have been checking in on. So take care of those 5. A lot of you have been omitting the practice problems, so please make sure you do those by tomorrow, because that's what we're going to be checking in class, and we'll have a graded assignment following, so make sure you're ready for it. Take care.